Alright, so now we're going to talk about inverses of matrices. Alright, so the first thing we want to talk about is what's referred to as the identity matrix. Alright, an identity matrix is a square matrix, so the same number of rows as columns. And we use notation, say like I sub I for identity, and this I sub 3, meaning it's a 3 by 3 matrix. And what it's going to look like is 1, 0, 0, 0, 1, 0, and 0, 0, 1. So you have these ones on what's referred to as the main diagonal right here, and then zeros everywhere else. And that would be the identity matrix for 3 by 3. You know, and I sub 2 would be 1, 0, 0, 1. Follow me? In general, it's I sub n. And that would be an n by n matrix, right? N by n matrix. All right, and just ones on the main diagonal, zeros everywhere else. That's called the identity matrix. Now, what happens if we take the identity matrix and multiply it times, another 2 by 2 matrix? All right, so A times I sub 2. Multiply these together. Can we even multiply these together? Well, yeah, this is a 2 by 2. This is a 2 by 2. Right, remember these are the same, so we're going to get another 2 by 2 over here. Alright, so you multiply it. 2 times 1 is 2, plus 0, so that'd be 2. And then 2 times 0, so that'd be negative 1. And 3 times 1, plus 3 is 3. And then 4. You get A back. That's why it's called the identity matrix. If you take another matrix and multiply it times the identity matrix, provided you can do that multiplication, then you will always get back your original matrix. Same situation if you were to if you could do that multiplication. Again, you're going to get back A. And this is the matrix version of, say, like our number 1 in the real numbers, where if you take any real number, multiply it by 1, you get the same number back. Well, this is the same idea, just in terms of the matrix world. All right? Alright, so now let's move on to a little note. Alright, so suppose we've got a 2 by 2 matrix, A, right? And suppose that determinant is not equal to 0. Remember, this is the notation for determinant. Then the inverse matrix of A is, the notation we're going to use for the inverse matrix is A to the negative 1, like that. And capital A means we're dealing with a matrix, right? And that's equal to 1 over the determinant of A, that's why the determinant of A can't be equal to 0, times another matrix. Everybody agree this is going to be some scalar out here because the determinant of A is just a number, so this is going to be some scalar. Now the matrix you're going to multiply that scalar by is, well, from your original 2 by 2 up here, the numbers on this main diagonal, the A and the D, they switch places. This is D, this is A. The numbers on the other diagonal, they change sign. All right, now I didn't derive where this is coming from, so if you want to see that derivation, you're going to need to talk to your instructor. Right, so this is how we calculate the inverse of a 2 by 2 matrix. Make note, this is only for a 2 by 2 matrix. 1 over the determinant times, and then you switch the numbers on the main diagonal, they switch places, and on the other diagonal, you switch signs. All right, let's do an example. Alright, so here's 5, 7, 2, 3. The first thing I would do is figure out what the determinant of A is. Alright, so remember how to find the determinant. So 5 times 3 is 15, minus 2 times 7, which is 14, gives you 1. Alright, so the determinant's 1, which means we now can find the inverse of this matrix. So A inverse equals 1 over the determinant of A, which is 1, so that's just 1, times, alright, the numbers on the main diagonal switch places. This is a 3 now, this is a 5, and the numbers on the other diagonal switch sign. And when you do that, you obviously just get back 3, negative 7, negative 2, and 5. Alright, now, what do you think happens if you multiply A times A inverse? Alright, so you get 5, 7, 2, 3. And 3, negative 7, negative 2, 5. Multiply those out. What do you get? That's right, you get the identity back. Okay, same thing would happen if you did A inverse times A, right? That would also give you the identity back. And you should verify that later, right? So, division of matrices is not defined, but this using the inverse, taking a matrix and multiplying it by its inverse, that will get you back to the identity. That we can do. All right, so make note that to find the inverse of a 2 by 2 matrix, it has to be a square matrix, right? Because you have to find the determinant first, and you only find the determinants of square matrices. So only matrices that are square can have an inverse matrix, but not every square matrix has an inverse, right? And that's the second note. All right, note the inverse of a matrix does not exist if its determinant is equal to 0, and that's because when you were back here, you'd be dividing by 0. Okay? So if B is equal to 5, 10, negative 3, negative 2, find B inverse. Okay, so first find the determinant. So B, which would equal negative 10 minus negative 30, so that equals 20. Right? So B inverse equals 1 over 20 times, all right, so what do we do with the numbers on the main diagonal? They switch places, so 2 and 5, and the numbers on the other diagonal change signs. So that's negative 10, that's positive 3. All right, so then we run 1 over 20 through, because it's just a scalar, so multiply it times everything inside the matrix there, and you get negative 1/10, negative 1/2, 3/20, and 1/4. And that is B inverse. If you were to take B and B inverse and multiply them together, you would get the identity matrix back. Right? I'll leave that for you guys to play with. All right? But that's what would happen. All right, so that's how you find the inverse of a 2 by 2 matrix. That's kind of the short way. The longer way, which can be used to find the inverse of any size, 2 by 2, 3 by 3, 15 by 15, involves the row transformations. So I'm not going to discuss that here. It kind of depends on the class that you're in, whether or not you will be discussing those methods or not. All right, that's all I got. Study well. Please let me know if you have any questions.